Hello, everyone. Good afternoon, good evening, good morning from wherever you're joining. Um, I'm very happy to introduce Professor Dr. Divya Srinivasan. She's McQueen Quattlebaum Professor in the Department of Industrial Engineering at Clemson University. With a background in human factors, motor control, and biomechanics, her research focuses on assessments and improvement of human health and performance in occupational settings. Over the last 5 years, her work is increasingly focused on investigating the effects of active and passive exoskeletons on human physical and cognitive demands and control strategies with the goals of improving both design as well as applications of these devices in diverse industrial domains. These efforts are variously supported by federal agencies such as NSF, NEOS, as well as industry partners in manufacturing, construction, agriculture, as well as emergency response. I'm so happy to have Divya Srinivasan here joining us. Please take over. Thanks for joining.
Thank you, KG. It's a pleasure to be here. Hello, everybody. I know it's a little bit late in Chennai. I hope you will stay awake and engaged with me as we go through this. Since we are a small crowd today, I don't want this to be a very formal lecture. So I'll start talking, but please feel free to interrupt me as many times as you want with questions. The more you talk, the more interesting it'll be for me to talk and the more you'll get from me. Since KG has already done the introduction, I'm going to go in. Before I start talking about the science of what I do, I thought it'll be fun to just sort of show you my journey on where I started and what I did over the years. So I was in India, in Chennai, getting my BE in Tripoli in 2005. Yeah, thankfully the slide says that it's been a while. So I graduated in 2005 from Chennai. And then I went to the University of Michigan, Ann Arbor. When I went there, I wasn't really sure on what I wanted to do. So I went there just for a master's degree in biomedical engineering. I was very nervous because in those days, there was nothing other than ECE, EEE, CS, and IT available. So biomed was something new, and I wasn't sure how it would pan out. But over my master's degree, I sort of just wanted to have fun and explore, what all is available in some new field like that. So I spent a few weeks like rotating between labs. I went into like bioinstrumentation and tried to like discover what was happening there. Then I went to a bioimaging lab, I remember, with huge MRI machines and whatnot. And so like while I was rotating through all that, I looked at some cellular technology stuff. And finally, I discovered biomechanics on my sort of fourth rotation among different things. And I just fell in love with biomechanics and I've stayed there since 2005. So as I was doing my biomed masters, the biomechanics lab that I worked in actually was at the intersection of biomedical engineering and industrial engineering. And the reason they had anything to do with industrial engineering was that the lab itself was creating biomechanical models, but applying those models in figuring out what could be done to improve the health and performance of industrial workers. So they had projects where biomechanical models would be applied to heavy force applications, push-pull kinds of tasks, and what sorts of risks they placed on people. And more interestingly, what engineering interventions could be developed to help improve those risks and or mitigate those risks rather. So on the way to doing the biomed degree, I thought, okay, maybe we should understand a little bit more about industrial engineering too. So I did some courses that overlap, but some specific courses in industrial engineering and got a master's in industrial operations engineering also. By that time, it had been 2 years since I started. So I sort of stayed on and got a PhD. So I graduated with a PhD from the University of Michigan in 2010, focusing on biomechanics and ergonomics. When I graduated, I still wasn't sure what I wanted to do with my life. I didn't know if I wanted to go into industry or academia. I did a few internships through my time at Michigan. I interned for some medical device companies, Boston Scientific being one of them. I did some things completely outside of engineering, actually, because when you go through 5 years of graduate school, you're wondering, what am I really doing with my life? So I did many things that had nothing to do with my graduate studies. But eventually I decided to actually go and do a postdoc. Um, my postdoc was actually set up to happen in Europe, but the process of going from America to Europe was so complicated in terms of all the visa and the paperwork that I needed to do. So in between, I spent around 8 months at the University of Washington, Seattle. Here, rather than being in engineering, because of all the industrial worker health and kinds of applications that I was exploring, I was invited to be at the Department of Occupational and Environmental Health Sciences. So I went there as a research scientist for 8 months. I was still doing the same work I was doing in my engineering degree. Funnily enough, it was a completely different department that was even outside of engineering that was hosting me. On from there, I went to Sweden. Here I got a European EU postdoctoral fellowship to spend 2.5 years in Sweden. This didn't happen when I went there. When I went there, I went there in the middle of winter. It was not even South Sweden. It was somewhat like central Sweden, as north as I'd ever been in my life. And I remember thinking that winter that there is no way I'm going to survive here. So I remember telling my postdoctoral mentor that you've had me for 6 months and then I'm packing up from here and leaving. But lots of things happened in those 6 months and I got very interested in the work I was doing. So I actually happened to spend many more years in Sweden than I thought I'd be. Again, here I was in the Center for Musculoskeletal Research, which was outside of engineering. It was also hosted in an occupational health science department. But after some years in Sweden, I think we were tired of the cold. We also, other things happened. I was no more single, I was married, I had children. So I started thinking differently. So I came back to the US. I came in 2016 and started as an assistant professor in industrial and systems engineering at Virginia Tech. I stayed there until 2021 and oops, I don't have another sort of mark here, but last year in 2021, I moved to Clemson University. I moved here as a full professor with joint appointments in industrial engineering and bioengineering. It's like life has come back a full circle, just like my PhD. Now I have two appointments. I still do very similar work to what I started my PhD out in, and I'm going to talk about that work for the rest of this talk. But before we go there, does anyone sort of have any questions on the pathway? Or do you want to just introduce yourselves and tell me a little bit about which department you're from and what you do? We are a really small group. Like I said, this can be a conversation. We don't need to make this more formal than it needs to be. I see Aishwarya, Shruti, Bhavya, Vriksha, all of you have joined since I started. Do you want to introduce yourselves?
Yes, ma'am. I'm Aishwarya. I'm in the computer science department.
Computer science, you said, Aishwarya?
Yes, ma'am.
Very good. Welcome. Anybody else?
Hello, ma'am. I'm Diksha, and I'm also from computer science.
Hi, ma'am. I'm Shruti. I'm also from computer science.
Thank you, Shruti and Riksha. Bhavya, Sai, can you unmute yourselves? Is it possible to tell us where you're from?
I'm Bhavya, and I'm also from computer science.
We have a big CS crowd. That's cool. Okay. We'll move on. I don't know how much of computer science stuff I'm going to touch, but I'm going to keep this pretty high level so you can see, and this will still make sense to you even if you were not from bioengineering or electrical engineering. So, okay. Sorry, I pressed the wrong button. Let me move on to describe a little bit of what I do. So my research falls into several different buckets, and maybe this is not that interesting to you, but I really like what I do. So I'm going to bother you with some details of what I do. The first bucket you're seeing here on the left top of your screen talks about gait biomechanics and postural control. In a nutshell, what I do basically is that I like to study how people move. You know, what sorts of movement patterns do people employ and why is that interesting? Because based on that, we can understand what their bodies are putting out, and we can also understand what the effects are going to be of them working under different circumstances. That's the analyzing the effects of movements part. But in why would an electrical engineer care about all this? Because I am very interested in control. And I study control not in machines, but in humans. So human motor control, as we call it, is something that's sort of been one of my passions from the day I started out my research. So I then apply these control models to figuring out how things happen in various environments, some of them being industrial, some of them have to do with sports, some of them have to do with medical rehabilitation. Those are the kinds of things I'll talk about today. So when we say gait biomechanics and postural control, this has to do with the balance control system in our bodies and how we walk and what sorts of control principles are applied while people walk. And you might wonder, why is this even interesting? Don't we know how people walk by now? Because even something as simple as walking, first of all, there are deep medical applications in the sense of assistive technologies and people that are not able to walk being, developing engineering interventions that can help them walk. From another perspective, the picture you see here in the slide is actually from one of our military projects, where soldiers are marching and marching and marching for several miles with heavy backpacks. So it was a study about backpack load distribution design, and also understanding what sorts of strategies people deploy while doing these long marches as they gain experience in military settings. So if you are an experienced, they call them dismounted soldiers, an experienced dismounted soldier, what sorts of things do you do to deal with the fatigue you experience on a day-to-day basis? And if we can learn that or somehow quantify that, the hope is that we will be able to train novices and cadets better. And why is that important? Because the rate of injuries among novice soldiers that haven't even made it out into the real world yet is staggeringly high. They report really high rates of pain and disorders in their lower limbs and their back. That's why we were doing a project like that. That's one part of it. The second part of it is that if you take industrial settings, people slipping and falling in workplaces is actually the highest cause of work-related disorders and complaints that, at least in the US, that's the highest cause of work-related problems. So yeah, that's enough about that bucket of research, gait biomechanics and postural control. The second part of here, the second hexagon here is on computer work and sedentary behavior. Over the years, I did quite a lot of work on everybody that sits in front of a computer for a long time usually talks about shoulder pain and neck pain, right? So even if you are not in this field, this is probably something you're super familiar with. We did some work on understanding whether these desks called sit-stand desks, they can be in a seated position or a standing position. They were brought into the working life by folks that were doing sort of metabolic research. So people that were interested in asking whether a standing desk will help you lose weight or become more fit. We were not doing that kind of research, but we wanted to know if the problems in your neck shoulder region can be mitigated by changing your postures while you do computer work and what that means and so on. We were also trying to develop guidelines for the use of the desks themselves. So if somebody gives you a standing desk at work and says use it, you as a user might be wondering, what am I supposed to do with this? Am I supposed to stand all day? Am I supposed to sit for 4 hours and stand for 4 hours? Am I supposed to raise my desk to a standing position once every 10 minutes? So what do I do with the desk, right? So this is an example of where sometimes these ideas like user-centered design, but also user training and making a user think on why this technology was developed the way it is and how to use it is something we apply in these studies in addition to ergonomics principles. That's the second bucket. The third bucket of research says repetitive work and fatigue. I don't know if that is very interesting to you all. I'm seeing a message in the chat about my background being very bright. I'm sorry, KG, that's coming from the window. I don't think I can do much about the light outside.
Yeah, I just thought to, sorry to disturb your flow, but yeah, I just thought I think this is even better. Yeah, thank you so much.
Okay, no problem, thank you. So repetitive work and fatigue, the context is that there are people doing what we call repetitive work in the industrial settings. So day in and day out, they have to do the same job again and again and again. When you do the same thing over and over again, first of all, it's horribly boring, but that's not what we are going to talk about today. in addition to being boring, even if the work is not excessively demanding, so you're not like pushing hundreds of kilos of load, it's not something that is supposed to be able to hurt you. But the fact that you're using the same set of muscles over and over and over again does cause fatigue and musculoskeletal disorders. So we've done quite a bit of work in that domain, asking what can we do in terms of work design or principles of working so that we can reduce some of those problems. Obviously, the ideal thing to do would be to remove repetitive work away from the work environment completely. And that's the idea when you introduce some kind of automation or robotics. But given that there is some repetitive work that still is sort of sustained even after all these interventions, what can we do is the question there. The central hexagon in the slide has to do with neuromotor control and performance. This is sort of the core work that I do, or the core methods and theories that I work with resides in this bucket. So we have a nervous system that sends control commands to our muscular system, and our muscular system usually executes these commands. So understanding the interplay between the controls and the execution is what we usually call neuromotor control. And that's what I was deeply trained to do. Everything else is sort of what I developed around it. So here we are asking fundamental questions on how that control works, and to perturb the control and study how things can happen, you need to have some way to perturb, right? And this is not a machine. You can't just cut off like electricity or break a component. So instead, we look for natural settings in which we can infer that some of these changes happen. So there are gradual changes in people's control as they age. So then we can introduce age as a factor in some of our experimental designs and begin to understand what happens when there is a deterioration in some part of that control system. So we typically study the effects of factors like age and gender. Maybe you have a musculoskeletal injury, or you have shoulder pain or neck pain or elbow or knee pain or something around the joints of your body. So we look for those. First of all, the factors themselves are interesting and practical to understand, right? So you want to know what happens when somebody ages. That itself is something worth telling the world about. But in addition, asking those questions about age also helps us infer something deeper about the underlying controls models that we develop in the lab. So it's a sort of win-win scenario where the same factor is useful from multiple perspectives. So that's the central hexagon in my slide here. And the bottom two have to do about exoskeletons, powered and passive ones. And we've done a lot of work in that space, which I can't even finish talking about today, even if we take all the time we have. So let's see how much we get into that. Are there any questions or thoughts on what you're seeing so far? I know this is a little bit far from computer science, but it's okay. I mean, you can ask me questions that are not even about what I have in the slide if you would like to.
I always don't miss these opportunities just to tell other students as well. I'm curious, like, do you interact with doctors in nervous system related things, or like how easy it is to work with the medical professionals because of the cross-functional share?
That is an excellent question, KG. We would like to work with doctors on this stuff, but I think when we say something like the nervous system, there are various levels at which you can study the system, right? You can extract a neuron, or not extract it. You can study it at a neuronal level where it's much more sort of cellular and microscopic. You could study things where there is somebody has a stroke, or there are imaging things you can do inside a person's brain where the medical community is probably more involved. I would like to sort of say that we like to study the system as a whole and somewhat more from an engineering perspective. So we typically stay away from anything invasive. So we don't depend on technologies that need you to go inside a person's body and cut it open or image or anything like that. So in that sense, we like to keep studying more or less healthy people that we can deal with. When we say perturbations, they are more mild. I might make you very tired. That's it. It's not like I'm going to inject you with drugs or anything. So we don't have to depend on doctors for our research. And we like to keep it that way because when you involve medical doctors, the studies get very complicated, they get very expensive and very time consuming. So it's more of a practical sort of decision from our, not just me, from many people in our field, that we do systems level research, but in a way that engineers can handle it without needing doctors. We train our students in principles that have many things to do with the medical community, but still we are sort of self-sufficient. Does that make sense?
Yeah, yeah. I was trying to find what is the state of affairs like. It's been hard, and it remains. That's the way I see it. Yeah.
Thank you. Okay, moving on. This is, I said I have a primary appointment in the industrial engineering environment, right? So I thought I should talk to you a little bit about the industrial engineering side of this. So if you had a crystal ball to look like what the future of industries is, what could that be? This, I think, computer science students can handle as well. You are reading about all the innovations that are going on in the world, right? You are reading about robots and automation and AI and this internet of the future and whatnot. If I were to sort of give you that crystal ball and ask you what you saw inside, what do you think a future factory will look like? I'm not saying any industry, I'm constraining it. Have you ever thought about what a future factory would look like, or how you would like it to look like? You can say whatever you want. You don't have to be very shy, because there's no right or wrong answer to this question. It's really what you think will happen. Anyone?
Students, please participate. A professor is spending her time for us. Please participate. There's no right or wrong answer. The professor is just asking what a future factory do you think would look like? Will it have Hendir and Rajinikanth in there?
I think Aishwarya was trying to say something. Go ahead, Aishwarya. Thank you, Karthik.
Yes, ma'am. Probably a more like a completely autonomous process. Like you just have machines operating everything. There's very minimal human interaction, and yeah, basically everything is just autonomous by the system.
Very good. That's an excellent response. Many famous people around the world have thought the same thing that you have thought, and I'm going to show you that on the next slide. What else? Is there anybody who thinks it'll be different, or anybody that agrees with Aishwarya?
I feel if nano computing like booms, we'd probably get micro robots doing complicated invasive surgeries somewhere in the future, if not near or in the next 50 years or so, somewhere, sometime.
Wonderful, Vriksha. Thank you. What else? So far, we have heard autonomous robots, micro robots. What else? Any other thoughts? Shall we move on?
Humanoids.
Humanoids. I'm very glad to hear that. Okay. Anybody else thinks that humans would still be needed in a factory? No, we don't need humans in a factory. Anybody that wants to advocate for humans being in a factory?
Maybe humans would be required to take the blame all the time, even in the presence of robots.
That's a very wise thing you said, Karthik. I don't know where you work, but this was incredibly wise. Somebody needs to be actually, and this is a very, very real problem with implementing completely autonomous things in many places. Even if you automate a lot of something, or even if you made something super smart with AI, the issue that many sort of insurance companies and legal government is having is that If something goes wrong, who do you blame? If it's a fully automated thing, is it the company that implemented the autonomous solution? Is it the people that made the autonomous system? Is it the people that are in charge of hosting the data and figuring something out in security? So who to blame is actually a very real reason for, even if we have the technology, why sometimes we are holding back and keeping humans in charge. So great. Okay, I'm going to show you a few things about what I know about the future, and then we'll see what that means. Let's see. Okay, so this is a quote from Elon Musk. This was a few years ago when he said that Tesla factories would be completely automated and that they didn't need any humans on the floor. And then later figured out that yes, excessive automation at Tesla was a mistake. We really underrate humans, is what he said. This is actually the way that the industrial revolutions are progressing in the technological sort of scale. So we had everybody knows about the first industrial revolution, but then there have been more along the way that you may not have heard about unless you are in sort of an industrial field. So we have what is called Industry 4.0. That was the latest kind of thing where the focus was on the development of cyber physical systems. And cyber physical systems are intended to be not just AI and computing, but also bringing AI and computing into robotic systems. And that was the point. As Industry 4.0 was becoming more and more a reality, like over the last decade or so, several companies have realized that at least as of now, automation cannot solve all the problems, because if you, A, it's really expensive. B, given the current state of technology, if you fix a particular product line in a factory to be completely automated, and then you want to slightly change or introduce a variation in the production, it is really time consuming and expensive to begin to then customize these production lines to produce parts with, industries that manufacture high mix parts, or they have wide variations in size, oddly shaped components, and so on. So even within a manufacturing context, completely automating segments of production has been very challenging for those reasons. And then if you go into other industries like construction or mining, doing away with human decision-making, human flexibility, human dexterity, these have been deep challenges that all these industries have faced. So even as we have research on robotics and automation progressing on one hand, there are still industries that, almost every industry actually, especially because of COVID, is feeling the challenges of labor and skill shortages. So Industry 5.0 actually is supposed to be focused on, they changed the word cyber physical systems to cyber physical cognitive systems. So this supposed fifth industrial revolution, or Industry 5.0, which is sort of just kicking in right now, is supposed to be completely focused on the cooperation between human and machine. So can we have human intelligence working in harmony with cognitive computing? Can we put humans back into industrial production, but in such a way that they can work at tandem with collaborative robots? Can we upskill workers to be doing value-added tasks in production, so that things like customization and personalization for customers is something that we can exploit, or I shouldn't say exploit is the wrong word, leverage both human skills and robotic skills to produce, is sort of where the industry is headed. And while that's happening, there are a lot of concerns. And like I said, this is much worse actually after COVID. People are not able to fill jobs, skilled jobs in manufacturing. Millions of jobs are going to go unfilled is actually the sort of crunch that suppliers and manufacturing companies are feeling this is true of the Western world. I'm sorry that I didn't do research about what's currently going on in India right now, but I'm sort of also thinking that this is true over much of the world, that after COVID, people have sort of either forced to leave jobs or they've left jobs in a way that all supply demand chains and lines are getting hit. And this is one part. COVID has created an artificial sort of accelerator in this process. But even before COVID, the other thing that the world over everybody is facing is that our workforce is actually aging. So on one hand, we thought everything would be automated by now, and everything is not automated by now. And on the other hand, the average age of retirement, so the average age for how long people are in the workforce, is also going up and up and up. That's a good thing because people's life expectancy is increasing because of other technological developments. But if your life expectancy increases, then you also, as a society, probably want to be employed for longer so that you have a better economic end at given all these things that are going on. So people want to be at work for longer, but then are we doing enough things at work such that they can be employed for longer is an issue. And you might be thinking that everything is so advanced now or so well developed that nobody is still doing jobs that are physically demanding, at least in the Western world. Well, that's not the case. Even now in the US, billions of dollars are being spent on overexertion injuries, which means that people are doing physically more than they are supposed to be doing. They're handling more forces, either for lifting or pushing or pulling, very manual things that you would think we have designed out of the workplace. We still haven't designed them out of the workplace enough. And the amount of money that's spent on low back disorders in the US is, if you include like workers' compensation, the medical claims costs, all this stuff, it actually is more than the cost of what we spend or what is supposed to be costing for cancer or for AIDS. Like nobody talks about musculoskeletal disorders as something that is, a big medical problem or an expensive medical problem, but it is really expensive in terms of just PR production and costs and so on also. So if you think about all that the future is having to deal with, yes, we'd like to automate everything if possible. There are social questions. Then what do people do if you've automated everything that we are not dealing with today? But we are seeing right now that even at Industry 5.0, we are not going to be able to automate everything. So if we don't automate everything, then what are we doing? We want to bring in robotics. Like, don't mistake me. I'm not saying we should go back to people doing everything by hand. The question now is, can we integrate robots in an agile and flexible way such that they can work back and forth with humans? And then what should those design principles be? How do you design robots that are safe, efficient, that can communicate back and forth with a human in a productive way, both for the human and for the robot? And finally, how do you design the workflow? What should be done by a human and what should be done by a robot? If you put them together, how do you take the best advantage of both systems such that each one can be doing what they are good at and what they can keep getting better at? Those are sort of the challenges facing the industry today. Any sort of comments on where you thought we would go and where we are sort of headed? So my take on this is that we still have a worker very much at the center of a good factory and the future of work, as we call it. We just want to be sure that this worker can be healthy, can be safe, can be skilled, and can also be productive. We don't want our workers doing what we call like dull, dumb, dirty jobs. We want to give them the best that there is to be given, but we are still very much in a place where we are not doing away with workers yet, even on factory floors. And that's just my take on this, both as a person in the field, but also based on what I've been seeing going on. I'm not going to stop and keep asking about your comments, but if you do have comments or questions, please stop me at any time. Let's move on.
Sorry,
So, yes.
if it's all right to ask a question that came up. And so the automation and industry, and I'm not a manufacturing person. So one question that comes is, usually manufacturing is considered very employment friendly. And I mean, you want to increase manufacturing to improve a country's economy and so on, to employ a large number of people. But usually the counter to it is whose technology at whose place, or taking away some of the low-skilled jobs and giving it to tech or robots. Basically puts other set of people in control from one. So the question that comes to mind is, are there, or from your expertise, is there any focus on with this kind of an automation? the employability or being able to employ a large number of people, is that a kind of problem area that your research or any research focuses on?
That's a really good question, Karthik. So you've asked many good questions. I'm going to try to answer a few of them. I think that it is a big problem that we call it worker displacement. So if you take away the low-skill jobs, and you might create new jobs, which is what everybody in robotics says, right? Like robots are not taking away jobs, it's just changing the jobs that people can have. The first truth of the matter is, if you take away 1,000 low-skill jobs, are you going to create 1,000 high-skill jobs? Probably not. Probably the number of high-skill jobs is going to be lesser. Now, then the question that you ask is, what happens if you take away a low-skill job and create a job where somebody is supposed to control a semi-autonomous robot? The skill level that will, or the kind of skills that were needed here and the kind of skills that are going to be needed in the new job you created is completely different. And yes, there is a lot of good money being spent by various agencies around the world today on this concept of reskilling workers. We are talking about robotics and automation as good things in terms of productivity and bottom line and so on for manufacturing outputs. If we do that, workers are going to get displaced. And on the other hand, as we do these robotics and automation kinds of changes, we are creating these new segments of jobs that we are not able to fill because people don't have the training to get into those spots. So what can we do as a society or as whoever in the field to bring up training programs that will take people in at one level in an industry and either make them more well-rounded so that they can fit a few other spots as needed and keep rotating? Or is there some kind of more consistent, what we call like a reskilling program in a company where you could start as probably a machinist, but then as you move forward, you have opportunities periodically to keep either revising or retraining or even upskilling computer-based and robotics-based skills as you go through. And everybody understands that that is going to be needed. The most efficient way to do it is programs like that going to be based in like universities, technical colleges, community colleges, or at the factory? Who's going to create them? Who's going to sort of develop them and pay for them? Those are the conversations that are happening. Does that answer your question?
Wonderful. Thank you, Divya. Yes.
And I think since we have so many computer science students here, you may be interested in knowing that the idea of using mixed reality based technologies like VR and virtual reality, augmented reality, or some kind of mixed reality to create these environments where people can be at their jobs and get trained in inexpensive but efficient ways is a huge field right now. If you can think about using virtual reality to train a surgeon for surgical skills, or for training a factory worker in some complex assembly process, or a maintenance operator in maintenance operations for complex equipment, those are the kinds of things that people are pouring millions of dollars into studying and developing at this point. So that's just a plug for a field of research right now. And I mean, I should place it in context. It's not like training somebody in virtual reality is the same as training them in person. The point is not to replace it. The point is to ask whether we can reduce the in-person training hours and requirements by at least a bit because we can train them through other modalities. That's what I'm talking about. Karthik says that a CEG alumni startup, RAPL, is working in this area. That's fantastic. Go to the chat if you want to learn more about that. The message is in the chat. Okay, now I'm going to come back to the thread of what I was talking about. This is great. I'm loving this back and forth conversation. In terms of human-robot collaborations, that is sort of one of the fields that I work in. I talked to you about biomechanics, then I talked to you about motor control. Why am I studying human-robot collaborations? Because unlike human-computer interactions, HCI was what is a sister field to this field. In HCI, you're talking about humans and computers exchanging information and how you can promote the exchange and collaboration between the two systems. In HRI, human-robot interaction, now we have a robotic system. And then if there is going to be some exchange between the two, it is not necessarily only information that the two exchange, right? So if the robot is completely autonomous and is a separate entity, maybe you and the robot are only exchanging information. Even in such systems, nowadays, there are examples where the robot is not housed in some cage in the factory where it does its own thing. Maybe the robot and you are working at tandem. So think of an assembly process the robot is doing something and you are doing something, and maybe there is a dependency between you both, that the robot assembles a part and hands it over to you, or vice versa. That's one example of a human robot collaboration scenario where you each have independent goals, but you are somewhat dependent on each other, at least in a sequential way. A second example of a collaborative system would be where you and the robot are probably tackling different ends of the same problem. So imagine moving a somewhat heavy component, but also having to precisely and dexterously manipulate it to place it somewhere. So the robot can provide the force you require to navigate or move that component, but then you as the human can manage the dexterous manipulation of where it should be placed and how it should be placed much better than a robot. So maybe you both are working, but manipulating a part or a piece together in a factory. So this is the next sort of level of collaboration where you're co-manipulating a part. The third level of collaborative systems, a good example is an exoskeleton. We call them wearable robots. You're actually wearing a robot. The robotic system, maybe you're wearing a bunch of robotic arms or robotic legs that give you sort of extra human capacities, but you as the human is responsible for the net output of your systems together. So you are still navigating, you are still sort of deciding what needs to be done. The robot is simply assisting you or increasing your physical capabilities when you do those things. Why would we do this? Because now it's not a humanoid robot for which you have to develop super complex algorithms to control it. It's not an autonomous robot. You don't have to solve the sensation perception problems. It's simply a robot you're wearing. You as the human have your skills, your cognition, everything intact, and the robot is simply giving you mechanical assistance, right? So it somewhat displaces the control problems and puts them back on the human, which we are very good at solving, by the way, and simply gives the robot's mechanical capacity to us for us to decide what to do with it. So these are various examples of human-robot collaborative systems. And why is somebody like me in this field? Because if you are constantly exchanging physical objects or forces or controlling or co-controlling objects together, then the way the human brain would control our motion, or the humans would learn new things about their environment or their tools or the robots they're controlling, becomes super important to developing these collaborative principles. So that's why I sort of am in this field. And I'm going to talk a little bit more today about what we call exoskeleton systems. So these are wearable systems, wearable robots that work with a user. So you're wearing them and they can augment or reinforce or even restore human performance. So I've said two things here. Exoskeletons are not autonomous robots. So they are not about replacing the human in a particular space. They are about augmenting the human. The second part is they are also not prosthetics. So prosthetics or prosthesis are robotic components that are meant to replace a body part that you have lost. So if somebody doesn't have a limb, they could be wearing a prosthetic limb that they can control or that is smart or whatever. That's an entirely different field, but that replaces a body part. An autonomous robot replaces the entire human. An exoskeleton is not any of those. It is a system that you wear and you use. So why are we even interested in exoskeletons? Because the idea I briefly mentioned to you already is that as against an autonomous robot, whether it's on wheels or it's a humanoid, you're not making controls that would work to make the robot useful or good in every kind of environment or situation the robot could potentially face. You are using the mechanical capacity of the robot, but you as the human still has your skill, judgment, and sensory modalities intact to utilize that robot in whatever way you want. Obviously, the most glorious example of an exoskeleton that works really well is the Iron Man suit, except that we don't have any Tony Starks in the real world, but that's sort of the vision, right? We'd like to get there someday, even if not to fly and shoot stuff, at least to give people that kind of capacity in the situations they face day to day. So this is a little question about, are exoskeletons really new? Maybe this is laughably old for all the young children in the room today, but since the 1960s, the point I wanted to make is people have been fascinated with this concept of people wearing mechanical structures that would give them extra human capabilities. So from early on in the 60s, there's been this idea and some prototypes, really bulky prototypes that were developed, as you can see, over the years. And there's also been the idea of an exoskeleton even in popular science for a long time. So that's why I quickly wanted to show you that. So what is new right now, right? Why are we talking about exoskeletons so much more today than we used to in the past? And there are a few reasons there. The first thing is that we have to acknowledge the technological developments that have taken place in electrical systems, electronics, computer science, like battery technologies, control systems, and so on, such that making a mechanical arm with some significant capacity does not look like a giant structure that I showed you that was around in the 60s. So today it's even possible for us to talk about wearable robots because of developments in those fundamental fields that have helped advance technological capabilities, motors, actuators, cables, spring systems, battery technologies, and so on, to the extent that we can even think about a system that doesn't weigh 200 kilos that somebody can wear. So that's some development that's happened in that space, those spaces. The second part of it is that a lot of funding has gone into spurring developments in exoskeletons, specifically in the military and the medical domains, at least in the Western world. Many countries for defense applications were very interested in looking at whether soldiers could, have super soldier capabilities. So a lot of funding was injected into research in the space. Similarly, in the medical domain, not from the perspective of augmenting somebody, but from the perspective of assistive technologies and rehabilitation technologies, a lot of dollars have gone into sort of research in, if somebody cannot walk, can we, instead of putting them in a wheelchair, create an exoskeleton that they can wear and then go walking, right? So those kinds of technologies, they all led to these fundamental advances in several fields around this area. The idea of an industrial exoskeleton, which is that somebody who is healthy can still wear an exoskeleton simply to get a little bit more out of their bodies, right? That idea is very new. And when I say very new, it's probably less than 10 years old. I mean, not even 10 years. That's what I mean by very new. So now the questions for design, the questions for design requirements, and also sort of where the applications are going to be is very different when we are talking about industrial exoskeletons versus these other kinds of exoskeletons. So in an industrial setting, you probably don't need an exoskeleton that would give you the ability to fly, an exoskeleton that would be working even without battery in hazardous outdoor conditions for 40 hours, right? Like those are very military kind of requirements. We don't need that in an industrial setting. We also don't need an exoskeleton that can give you capacities that you don't have. For instance, assistive devices that help you walk, or maybe you are a stroke survivor who can't move your arm, but now you wear an exoskeleton that can then move your arm for you. We don't need devices like that either in the industrial domain. So that's what I meant by the design requirements are very unique to the industrial domain, and I'm going to go more into that. But the thing that I wanted to share with you on this slide is that this is sort of a good way to check out what's going on in the exoskeleton space. If you go to the website called exoskeletonreport.com, they maintain an updated catalog on what kinds of exoskeletons are being commercially available. These don't include research prototypes that are just sitting in somebody's labs, but as soon as a device becomes commercially available that you can purchase, then it gets cataloged here. And they even organize it nicely by medical devices, military devices, industrial devices, and consumer devices. What do I mean by consumer devices? If an exoskeleton is going to help you go skiing or hiking or running or participate in some sports that you wouldn't, I shouldn't say you wouldn't have been able to, that you could get more out of just by wearing an exoskeleton, those kinds of devices get called consumer devices. So I've said a lot about exoskeletons and human robot collaborations. Let's take a short break here. Questions, comments?
I have a question. Space tourism is coming up, and is there any interest on that related to exoskeleton?
Sorry, KG, what did you say?
Space tourism.
Space tourism. Wow.
Like spacesuit itself, do you think it's an exoskeleton, or where does the boundary lie? Like anything on top of humans is exoskeleton, or
that is a really excellent question, because I think many of the exoskeleton designs are actually inspired by spacesuit designs in some ways, right? So if you get into the design here, you're asking what is the lightest and the most sort of efficient material you can put on somebody that would be having the capacity to withstand all the torques you'd be applying. So in that sense, that is one part where spacesuit design has really inspired the research. The other part is you're asking practical questions on the sizing of components such that it would sit as well on me as on you. We call that anthropometry. That is also inspired by spacesuit design. But the answer to your original question is, yes, I think space organizations are very interested in asking, when people put on a spacesuit, are there components that we can attach to the spacesuit itself that would increase their capacity by a little bit, even that tiny bit, right? So absolutely, there is interest in space organizations. They don't get called exoskeletons because there are many terms floating around in the space. An exoskeleton, to be very precise, is a rigid mechanical structure that goes on somebody and gives them these assistive capacities or augmentation capacities. The same thing, you could achieve a little bit of it by embedding special fibers in textiles, for instance. So if it's a soft textile-based component that would still increase your capacity by even a little bit, those systems are called exosuits. And there is a big sort of market and research area around what can we do to the design of textiles, or what sorts of elements can we embed in not just space, but anything that somebody would wear that would give them something extra from wearing it. So yeah.
That's nice. Yeah, it's a spectrum I could see now. Like it starts with very big things that we can see visually to very small things that we don't even notice. Yeah.
Right. I mean, the people embed small things in socks nowadays, and the socks give you a little bit more springiness than they would have normally, right? So is that an exosuit? Nobody would call it an exosuit, but no, not every exoskeleton or every exosuit has to be something that encompasses the whole body. They could be just a shirt, just a pair of socks, or anything like that, right? So the textile exosuit market is its own thing, where I think the pros and cons should also be placed here before you all. An exoskeleton, a rigid mechanical system designed specifically for this purpose, can give you greater capacity in terms of how much it offers you on top of what you can do. But it's very explicit, it's outside of you, and it comes with its own design and wearability challenges. An exosuit is something that would be more like you wouldn't even feel that you were wearing something. So it's better integrated with your body. But because the elements have to be soft and they have to be well integrated, they can't be very heavy. They can't have like explicit battery systems or stuff. So the capacity that they would give you would be much smaller than a rigid system. So they are more wearable if they're a soft system, but they also wouldn't give you like dramatic augmentations compared to what a rigid system would offer.
Sorry, I have a follow-up on that question. Since you talk about capacity, it's very unique to individuals. Like I might not have, and like, is there like a list of things like these are the capacities and where we can go? I'm personally thinking like what I have and not have something. So I was like curious, is there anything on that trend, like, you know?
If you're asking about different actions that you can do with your body and your capacities, that's the next thing I'm going to.
Okay.
Yeah, cool. Okay. Anything else from our students from Chennai? Okay, I'm still going to have some more questions for you all. So, okay. KG asked an excellent question. He asked about what capacities are we talking about, and people can have different capacities. So yes, not every exoskeleton system or an exosuit is a whole body system. Many of these actually, to become practical, are designed for a specific part of your body and to augment specific actions. So the range of systems you're seeing in the slide here are what we call passive systems. We call them passive because they don't have powered components. There are no batteries. There are no like control systems working behind these. They have simple mechanical components that help give you some assistance. So we're talking about like pulley, cable, springs kind of systems, which will give you a little bit more I'm going to actually talk more about what they give you. But as you can see, the first system here called the ExoBionic, these are all commercially available. So these are in the market. You can go and buy them if you want. The ExoBionic system on the left-hand side of the slide is what we call a shoulder support exoskeleton. So once you wear it, there are some springs here, and what they do is help offload the weight of your arms or any tools you'd be carrying anytime you do what we call overhead work. So when your arms go above shoulder level, if you can think about like holding this posture for some time or holding that posture for some time, you'll see that in a very few minutes, you get very tired. Even without holding a tool, just the weight of your arms are causing some significant need for energy and muscular activity around your shoulder regions. So what these systems do is that the springs on the system take up that load or take down that load and pass it down further to your back. So when you are doing overhead work, a system like that would help you not exert as much energy and muscular effort to hold on to a load or to do some work overhead. The obvious applications of this in the industry space is assembly. When you're doing automotive assembly or aircraft assembly, there are many jobs that require you to be sort of doing overhead with your arms and neck above. This system is intended to offload your shoulders and neck, actually, when you engage in postures and work like that. The next two systems that you're seeing on the slide are called back support systems. So these are actually not the levitate. I'll talk about the third system here. The SuitX BackX is a classical back support system. What this system does is that there are springs that engage at either side of your hips. So anytime you bend down to pick up a load, think of the system as wearing two springs that help you just spring back up. So the most amount of energy you spend when you do lifting tasks, for instance, is to work against gravity to lift the load up, right? So your back is working strongly to bring you back up, and people develop back pain routinely because of tasks like these. This system basically offloads or reduces the amount of effort you have to put to lifting the load by those springs that engage, right? So the springs get engaged when you go down the first time to pick up the load. And when you come back up, the springs are releasing that extra energy and reducing the demands on your back. So it's, as you can see, it's a very simple concept, right? Just a couple of springs that can be sort of engaging at the right time and in the right direction to help reduce the loading in the face of lifting when you need it most. So that's those are two kinds of systems. I don't want to go through every system we have here, but the idea is that if you think about the industrial space, back pain and shoulder disorders, these are the most common kinds of complaints that industrial workers have. And the reasons for them are what I described. So manual material handling or having to move heavy materials around the workspace that involves lifting and pushing and pulling is the predominant cause of back pain. Having to do overhead work with your arms raised above shoulder level is the predominant cause of shoulder pain. So these are systems designed explicitly to address those concerns while at work. So they are not Ironman suits. They are not meant to suddenly help you lift hundreds of pounds more than what you can do, but they are simply intended to offload the amount of effort you have to engage or exert in doing your daily tasks by a little bit. And how much is itself a research question, right? How much offloading is needed, and what does that mean to how heavy and or non-wearable the system will become, are the sort of more in-depth questions. But those are some basic principles. So as you can see, these passive systems are pretty much like backpacks you can wear. Today, they cost in the range of a few $1,000s. So somewhere between $2,000 to $5,000, you can purchase pretty much any of these systems. And they don't need power supply, so there's no question of batteries and charging and so on. That's the space. What are some constraints of these systems? So people have to actually understand how to wear them. So donning these systems and adjusting them such that they work well for you is a thing you have to work on, because the springs are outside of your body in these systems. The efficiency with which they will transfer that torque to you depends on how well fitting that system is to you. So understanding how to put it on and fitting it such that it works well for you is a big deal. And so will workers actually take the time to learn that and do that is something we are facing in sort of trying to implement these systems in a practical sense. The second sort of issue is it is an extra load on your body. So especially if you think about Chennai, wearing a system like this is going to make you that much hotter, and maybe if the system is not helping you like it should, just lugging around that extra weight can make you more tired than you would have had you not had the system. So those are some details we are working with. The third part here is you see how these systems have components outside of your body. So if you think about a complex like industrial setting, will those parts get caught somewhere when you weren't thinking about it? Will they scratch a part that you were working on? So kind of safety concerns in a field, in addition to having something protruding from your body. It sounds very minor, but it's actually not that minor when you work in a factory. So those are some concerns. I think the pros are that the system can help you by offloading your muscle effort during specific actions. The cons are that in the process of doing that, they can create some other kinds of things that we weren't thinking about originally. So those are some simple things about these systems. The other side of this is what we call powered exoskeletons. So here, these are systems that can work only on a particular joint in your body to help a single action, like the passive systems, or they can be whole body systems, which can have multiple motors, actuators around the major joints of your body and can help you, with several different actions that you may do. The CRAEX system that is shown on the left-hand side is a back support system. So it is basically doing something like the BackX that I showed you on the previous slide, except that because it's powered, it has more capacity. It can assist you more. The second is that because the back support system, the passive system just has springs, it can only support you during specific phases of motion, right? Like the springs will get engaged when you go down, and then they will act when you come back up, was a simple principle I just explained to you. When you have a powered system, you can engage it, or you can make the motors work and assist you in everything you do, right? The motors can assist you when you go down, they can assist you when you come back up. That's one advantage. The second advantage is that because they are motors that can be programmed, you can also switch the level of assistance different people would want, need, or like based on their personal preferences, as well as the tasks that they're engaged in. Maybe if they're lifting a 50-kilo box, they would want the system to behave differently than if they're just bending down to lift a few kilos, where they don't want the system to be activating too much, right? So those are things that can be programmed into the motors. Then the research questions become interesting. What is an optimal assistance profile? How do you program that such that it can work for every person in every action they'd be doing? Should we embed some AI into that control system so that it can observe what the people do, classify activities, and learn to assist them as they would prefer? Or should we have something else? Like those are that's where it's heading, down that direction. When we come to the powered system, the full body system, the challenges are totally of another level, because the system is assisting you throughout your body. We are not just talking about offloading your muscular effort anymore. We are talking about significantly enhancing your capacity. So in a back support system, just a back support system, we should not be telling people you could lift 20 kilos without an exoskeleton. Now that you have an exoskeleton, go and lift 100 kilos. That's not what those systems are meant to do. Those systems are meant to relax your body and make you do a little bit less, even when you're just lifting the 20 kilos. A whole body system, on the other hand, has more powerful motors, and it's assisting all the joints in your body. This system that I'm showing you here specifically has the capacity to help you lift several times more than what you'd be able to do. So normally I can't even handle a 20-kilo box, but I can get into that system and lift something that weighs close to 100 kilos and feel like I'm only handling, 10 or 20 kilos, because everything in your body is assisted in a system like that. So that's the potential. Those systems can give you that kind of a superhuman capacity, make you do something you could never do before. But then the control challenges are way more complex in a system like that. Now we are not just talking about controlling 2 or 3 motors. We're talking about controlling over 20 degrees of freedom around the body, and how do those coordinate with each other? What happens to your ability to normally control your body versus when you're in this system? And there are several other research challenges down that way. But this is like a sampling of where the technology is in terms of rigid exoskeleton systems in the industrial domain, starting with like simple passive all the way to super complex powered. KG, I have a question for you here, actually. I see that we are just over the 1 hour mark. How much longer can we go?
I think we planned it for 1.5 hours,
Okay.
15 more minutes, if
Okay.
it's okay. Yeah.
Okay, yeah, it's completely okay with me. I'm not even halfway into my presentation, but I'll not try to finish it today. Just checking. Okay, any questions from the students so far? You're all in computer science. Do you see some opportunities for AI, for VR, for training? Is anybody doing human computer interaction stuff that seeing all this is exciting? No? Nobody sees any computer science applications here? Then I want to ask you all a different question. Since most of you are third years, have you sort of figured out what's next? Is there anybody who's interested in going to graduate school? Are you looking for jobs? What does it look like from your side?
I want to pursue graduate school, but I'm not sure if I want to do it immediately. So I think I want to get a couple of years of work experience and then pursue further.
Sounds good, Aishwarya. Thank you for sharing that. Anyone else? We have a very quiet room. Karthik, my recommendation in future to you would be to maybe ask the students to also turn on their cameras so we can at least see their faces when we talk.
Thank you, Divya. Wonderful feedback. I think Professor Gerald in his the first ever session, from then on, there was a recommendation. I think students are still shy or something.
Okay, cool. All right, moving on. Our research, to go more into detail, is basically asking a lot of questions on do these systems work, and our understanding of whether they work or how well they work is usually used to improve the design of these systems. So we are looking into what does it mean even for a system to work. Maybe it's reducing the load on one part of your body, but then is it just transferring that load to a different part of your body? What does it do to your movement strategies? So maybe you would use a certain way of lifting that has been trained in you and taught for you in the days before exoskeletons. But now that there are exoskeletons and you want them to sort of offload you best, is the same way of moving or working still applicable to the new enhanced or rather augmented experience? And then we are looking into, I told you that all these devices come with a certain weight, right? So if I tell you that it can reduce your back muscle effort by some X% when you bend down and lift a load, but then the device itself weighs 5 kilos and you are only bending and lifting loads so many times in a day, is it worth for you to wear a device that weighs something extra and walk around? So we asked that question through how much energy are you expending doing your work over a shift or a day with and without these systems to figure that out. And the final thing here, balance postural control, is lifted because if you have a system that is sort of artificially adding forces and torques around your body, you may very well imagine that sometimes you could get perturbed, right? So if you're trying to walk and the system is moving your legs in a different way, is that going to cause any challenges to your balance and postural control? So those are some common metrics we look at. In terms of people's actual usage of these devices. That's what is called others in this category. So even if a system is super functional, and this might make more sense to folks on the HCI side of this, if there's anybody like that in the room, just because something works, it doesn't mean that people will actually use it. So a system can work really well in terms of, how it was designed and its mechanical capacity, but if it's not comfortable to wear, if it's not easy to use, people are not going to adopt the technology, right? So there can be a super smartphone, which is very non-intuitive to use. Then the phone can be very smart, but nobody understands how useful it is. And so nobody likes it. And I think the famous companies like Apple, for instance, when it came out with its iPhone design, in terms of user design and user preferences, they had done so much that it just took off, right? So there's a lot of work to happen in that space when it comes to exoskeletons, because even with all the fantastic effects of many of these designs that we see in the lab, when we try to implement them in a real factory floor, for instance, the adoption of those devices is very low. And that's a challenge that the field is trying to tackle as of now. And if you need some special skills to be able to use the device well, especially if it's a powered system, maybe you need to understand the controls in some way, or you need to be comfortable with the idea of some other system powering you. Those are also, what do we need in terms of skill training is also another issue. And the last is what KG referred to sort of in some question earlier on. People have different capacities. People also have different preferences in what they would like on their bodies, right? So how are we going to design these systems such that they can work well for a diverse range of individuals, whether they are different sized bodies, different kinds of personalities, different ages, genders? Those are all some big questions in the field that we are trying to tackle. And where am I? Here. So this is probably going to be my last slide, and I want to sort of take some time to talk through this, and we will stop here. So in terms of what we do in research, I think I mentioned that do they work and what metrics should we use to decide whether they work is something we are still trying to figure out. Whether that should be objective by mechanical measures, whether they should be subjective based on like user preferences and comfort and things like that, or should we study somebody's performance when they do the same job with and without exoskeletons? Those are the kinds of questions we're still tackling. And this is critical, not just for saying, yes, this device works, or no, this device doesn't work. It's more nuanced in the sense that we are trying to iteratively improve the design of these devices. And we are also trying to improve their adoption in the industry levels. So we work both from the technology developer perspective, and we also work with the sort of end user perspective on both sides. That's the first bullet here on quantifying effectiveness. The second here is on determining use cases. So when I told you the basic working, like fundamentals of the exo, I told you that, oh, this back exo, if you bend down and lift a load, the springs engage and they disengage and things like that. But in the real world, nobody has a job where they are simply bending down and lifting a box that is in front of them all day. People are engaged in a variety of tasks. So extending the mechanical or the controls principles from like ideal tasks in a lab environment to actually figuring out what tasks in the field, like who are the workers that should be wearing these exoskeletons and what are the tasks for which these exos will help them, is a much more complicated question. But then trying to match design principles with those application principles is what is captured by the second bullet. In our case, a number of companies here actually want to use exoskeletons. They find the idea very cool that instead of losing their workers to, musculoskeletal disorders or fatigue or other factors, they actually could buy something that would help get their workers healthier, keep them in the work for longer, and maybe even make them more productive. But then the question they have is, they don't know where to begin. So who should we give these exoskeletons to? How many should we buy? When should they use them? How should they use them? Those are the questions we get asked. That's all the second bullet. The third bullet here about understanding field adoption is now outside of just the mechanical or the control principles. They are a little more on the side of how do you even get an implementation successful? And this is more like industrial engineering. because maybe there is a culture in a work environment where if somebody wears an exoskeleton, another worker will say, oh, you can't even do your job on your own without having an assistive device now? You must be pretty weak, right? Things like this happen in the real work. So people's perceptions of each other affects a lot about their decision whether they want to wear a device or not. Contrast that kind of environment to another environment where the fact that one person has an exoskeleton is seen as so cool. Wow, you're wearing this new robot. I wish I could get one. And both these kinds of environments exist. So the structure, the organizational culture, what your management thinks about you, what your coworkers think about you, how can we get these sorts of technologies understood the right way and get them deployed is a big area there. For instance, in some companies, workers are worried that if they're given exoskeletons, because it costs the company something to buy them, maybe suddenly they're expected to work for longer or they're expected to produce more. That is a concern that workers have sometimes. And in some settings, the situation is like, should we tell the workers, management has these questions, should we tell the workers that this device is going to improve their safety, in which case we can make it like personal protective equipment. If you make it like that, everybody has to wear it. So for instance, if you go into a construction environment here, everybody has to wear a safety hat, they have to wear safety glasses, they have to wear safety boots. Those are all required because they are considered PPE or personal protective equipment that you have to wear when you are at work. Now the question is, should an exoskeleton be called that, in which case everybody has to use it? Or should they be told this is a tool that can potentially help improve your safety or health or performance, and you have the choice whether to use it or not, in which case some people may use it and some people may not. And that itself is like a big deployment kind of question we have right now. As a researcher, I don't have like a vested interest in whether this gets applied or not. So then my question is, do we have enough evidence from all the research we do to tell that this device can help every single person in every single thing we do, which is the case that it should be if we tell them it's PPE? Or are we still far away from there? And do we want to tell people you can still voluntarily use it if you think it helps you, until the technology improves to a point where we are confident in saying, for this job, everybody should wear an exoskeleton because it's supposed to, I mean, it does help them. So those are the kinds of questions we tackle. I have a few sort of icons spread around the slide on many partners that we work with in this field. Some of them are our sponsors, some of them are those that we engage in collaborative research with, but I thought it'd be nice for you all to get a sense of like, is it only a particular company that cares about it? Is it only the medical industry that cares about it? No, like it's pretty widespread in terms of where exoskeletons are today and who is interested in them. So with that, I'd like to stop the presentation and thank the CGANA board for inviting me here. Thank you, Karthik. Thank you, KG. I'm still here and we have around 10 minutes left. If anybody has other questions, like questions about this or questions about anything at all, I'm here and happy to continue to chat with you.
And thank you, Divya.
Yeah, this is really nice. Thank you for sharing it, and a lot of resources to look into. Those were very useful.
Thank you, KG. Thank you, Karthik. Students, anything?
With this, I'll stop recording and then we
Sure.
can continue.
Sounds good.